Hello, everyone. Thank you for joining us today. My name is Jeff Jensen, and I work with FluoroFinder, the online experiment design platform for flow cytometry, and I'll be acting as your host for today's event. The webinar today is entitled An Optimized Method for Accurate Spread Measurement and Its Use in Panel Design. Before we get going, I want to point out that this webinar is being sponsored by BD Biosciences. As a leader in the flow cytometry industry, BD brings products and services to the research community that you just can't get anywhere else. The knowledge and expertise that BD brings to the field is unparalleled, and I think it's fantastic that they sponsor content like this to be shared with all of you. As a reminder, today's webinar is a live event. There will be a question and answer period at the end, but please feel free to ask questions during the presentation by using the GoToWebinar control panel located on the right side of your screen. The webinar today is being recorded, and a link to the recording will be sent out to all registrants. If we could get a few people just to type in hello or something into the question field or chat field, just so I can test to make sure that you can hear me and that that's working, I'd appreciate that. Great. All right, perfect. Hello, everybody. Oh, very responsive group. All right. Okay, super. So to get going today, I'd like to introduce our presenters. First, we have Mikko Corselli. Mikko Corselli has over 15 years of academic and industry experience in the development of flow cytometry applications. He received his PhD in clinical and experimental hematology and oncology from the University of Geneva, Italy. He spent 2 years at the University of Pittsburgh as a research scholar before continuing his research as a postdoctoral fellow at the University of California, Los Angeles. Mirko is currently the Global Scientific Marketing Manager at BD Biosciences. And next we have with us Bob Balderas. Bob Balderas has 40 years of leadership experience in both academia and the biotechnology industry, and he is recognized in the field as an immunology and flow cytometry domain expert. He's made significant contributions as a corporate scientist, site manager, and marketer. Bob has championed multiple successful key product launches during his tenure at Pharmagen and BD Biosciences, given more than 1,500 scientific and technology presentations, and is recognized for his success in creating critical collaborations with scientists to generate products that are relevant to BD's customers. In addition to being a distinguished fellow, Bob is currently the VP of Biological Sciences and VP of Market Development at BD Biosciences. Thank you, Mirko and Bob, for being here, and BD for presenting all this. And I'm going to go ahead and hand this over, I think, to Bob Balderas to give us a little more formal introduction here.
Okay. Thanks, Jeff, very much for the introduction. It's very kind. And welcome, everyone, to our program today. You know, it's always a great pleasure to take time with everyone. You know, we're all focused and we hear so many different things, you know, and are connected to our computers, and here's one more of them, but a very, very important one. You know, what has become a tradition at BD for many years is the time we take to focus on education and on fundamentals of flow, on the biology, on the platform itself, on color, the introduction of new colors, how to build a panel, and all the idiosyncrasies that go into it. And we realize the complexity of the types of studies that are out there that you do every day require more and more knowledge all the time to have a better understanding of, you know, how to build that panel and how to bridge the color with the right biology. Well, the program that you're going to hear today is one that continues in this direction of education, and it has a focus on a better understanding of an optimized method for accurate spread measurements, as it says in its title, and its use in panel design. And this topic is one that's very, very important. And again, it's kind of a process of education where we discover something and see something and use it, as we've used our spillover spread matrix for a number of years, until we get to a point where we learn something different and we begin to see something. And then it requires that depth of discovery inside to be able to unravel that information and to better put a new foundation on it. And that's exactly what Mirko has done for us. And it's just a great pleasure to have Mirko be able to roll this new concept, a new perspective out. But before we start, we've got a series of 3 initial poll questions that we would like everybody, if you'd like, to participate in. You're going to get some direction in just one moment. Each of these questions, though, that we have are there for us and for everyone to kind of gain a little bit of more information. And the first one is, when you run multicolor panels, what is your average panel size? And this is an important one, and I encourage everyone to get in there and put your idea on there and your vote. It helps us understand the audience that we have today, so that Mirko can move that perspective around. So please select one of those following. And in just a few seconds in here, we'll get Jeff to pull the information up so everybody can see where we are in that, and baseline this there. So you can see it's data that we can appreciate, and as a company, when we look at it, the majority of panels that individuals build are not up there over 18, 20, 25, 30, and 40, but we use enough colors or specificities to answer the questions that we have. But irrespective of that, the challenges of building that panel and on the platform that you're using, really matters. So let's go on to the second question that we have. And Mirko, can you advance that up for us? Do you use tools like the spillover spread matrix to predict spread and design your panel? This is one for myself that I'll make some comments in just a second after we see where everybody is. So again, an overwhelming majority of individuals that actually use that tool, and this is part of that process of education and kind of the inputs of information that we've got from individuals like Mario Roeder and others that have built a complete career around this. It's important. It's a great tool. But I think today, as we go through this, you're going to see something that recorrects it and helps us move in a different direction. So let's move to the last question before Mirko begins his talk.
Well, actually, I'm having some hard time seeing the results. So
Mirko, maybe you could come off your video.
Oh, yes.
1 second. There you go. Now ask that question, Mirko.
Sorry, Bob. I have a very hard time seeing the results on my screen. So if you could just give me.
Yeah, it was 64% actually used the spillover spread matrix.
Great.
Okay. So let's go on to the third question. Have you ever observed discrepancies between the predicted and the measured spread, resulting in suboptimal resolution of a population? Okay, let's see if Jeff can pull up the information for everyone. So the answer overwhelmingly is that 80% of you have seen discrepancies. And this is something that I saw too, and I build a lot of panels out there. And my tendency is to go to the real data and to look at it, and not to use a spillover spread matrix in the way that you might use it and that you can use it. Well, I guess right now we'll have a handoff in there for Mirko. Mirko, 80% of the individuals said that they see that discrepancy. So I welcome you to share with us the perspectives that you've seen and and look forward to the presentation and the questions that the audience will have. Thank you.
Thank you, Bob. And again, welcome everybody, and thank you for attending today's webinar. It's a pleasure to be here. And let me start by saying that I'm glad we asked those questions, because the bad news is that you are seeing discrepancies in your results. This might have an impact on your quality of the data. The good news is that we went above and beyond to really understand the root cause of this problem. And today you will learn why do you see this discrepancy, but most importantly, we will provide you with a new tool that eliminates that issue and will allow you to minimize the risk of wrong prediction of spread. But before we get into the depth of the presentation, just to level set, I would like to start from a brief intro on what is spillover, what is spread. And this is fundamental because we really need to understand what factors contribute to spread in order to have a clear prediction of it. Then we're going to spillover spread metrics, as we acknowledge that this has become and has been adopted now as a major tool to design panel, to predict spread, to assess your panel. But as we mentioned, there are discrepancies. So it's really important to understand what SSM is, but most importantly, what is not. And that will lead us naturally into introducing a new spread metrics that kind of overcompensates for this shortfall of these SSM, and how this is going to be a better tool for panel design and evaluation. So again, let's start from the basic concept of fluorescence spillover. Fluorescence spillover is technically the overlap, the spectral overlap of the emission curve of one dye into the emission curve of another dye. And what you can see, I think my slightly delayed. If you look at per CPSA 5.5, you will see that there is spillover, there is overlap in this area. That is the area of conventional flow cytometry where we detect the signal of PSI 7. Now, let's also start appreciating that spillover and spread, it's an innate characteristic of dyes and flow cytometry. Whether you are using conventional flow cytometry, where you are detecting only discrete regions of a curve, or full spectrum flow cytometry or spectral flow cytometry, you still have overlap of the curves. So spread will still occur in a spectral flow cytometry as well. So this is intrinsic to the use of two fluorochromes and two detection systems. But what this means is that if I'm running a single control of per CPSA 5.5, the instrument will detect signal in the detector allocated for PSI 7. So that would be basically a false positive signal, as you can see here. There's no PSI 7 here. We are reading something spilling over from per CPSA 5.5. And you can also see, because if you compare the negative population and you compare the signal into PSI 7, from the negative, it's just 12. From the positive population, went up to 3,000 because we are catching the signal. But luckily, we have compensation, and the process of compensation is by running single control, we instruct the software, the instrument, the algorithm to basically subtract this signal. And sorry, I'm slightly delayed. Maybe frozen. There you go. So when we compensate, basically we're bringing the signal down to a point that the true compensation is when the MFI, the intensity of the signal into PSI 7 from the negative and the positive now comes to the same value. So the centers of the two populations are aligned. However, one critical information is that while compensation brings the signal down and minimize this artifact, compensation does not eliminate spread. So you can see that even though these two populations have the same MFI in the PSI7, the positive has a larger width, a larger spread of the signal. So that's what we're going to deal with. And we'll talk about how this is important and why this matters. But it's really important to understand that when we compensate, whether we're doing that through conventional flow cytometry or spectral unmixing, we are not eliminating the spread that comes from the overlap of two dyes. So we will talk about how we can handle this, how we can deal this, how we can predict this to prevent that this will have an impact on our panel. So let's talk about the factors that influence the total amount of spread. And I really want to take a minute here because this is going to be a fundamental concept to understand SSM and what we're going to talk today. When we talk about spread in general, so the width of the positive population into a given detector, we know that this is a function of spillover. The more a fluorochrome spills overlap into another detector, the more spread you will have. That's pretty intuitive. So we're looking the same fluorochrome PE with a spillover of 9.8, 26, and you can see that there's a direct correlation between the amount of spillover and the spread that we observe. However, what is really critical to keep in mind is the spillover is not the only factor that influences the amount of spread. So if we go back to our PE into PCA594, the spillover into this channel, it's constant. It's 26.4%. That's how much overlap there is. However, the amount of spread, it's also a function of the signal of the PE signal, the MFI. So you can see that the higher the MFI, the higher the spread for the same exact spillover value. So I want you to start thinking of total spread. When we talk about total spread, there's the constant of spillover, and then you have a multiplier, which is the MFI. And then MFI, it's influenced by two factors: the brightness of the fluorochrome and the antigen density. The more receptors are expressed on a cell that we're going to interrogate, the higher the signal will be for the same fluorochrome, and that will multiply and increase the amount of spread. So there is spillover spread, that is the spread that comes from spillover, but if we want to look at the overall total spread, we also need to take into consideration the MFI and the signal that comes from that fluorochrome. Why is this critical? Because when we come to now resolve population, the spread can affect resolution. Let's say we have a dim population here on PCA594, not co-expressed with PE. There's no problem, we can resolve it. And maybe if the antigen on PE is expressed at low density, there's no problem either. But now if we're putting a high density antigen on a fluorochrome that spills into a detector where we have a dim antigen, we're going to have an overlap, background, loss of resolution. So there's a number of strategies that we can use. For example, we can, in this case, use a higher antigen density marker in PCA594 to pull up that population. But bottom line, the importance here is if we miscalculate or if we underestimate the amount of spread, by the time we run our sample and we run our true experiment, we might find ourselves in a situation where we cannot fully resolve the population that we want. And this is exactly an example. So this is the same exact sample run on the same exact instrument the same day, just two different panels, okay? But just by choosing different combination of panels, of fluorochromes in this panel, we get completely different outcome. So you can see, you can appreciate that this is a beautiful resolution of PD1 and CD57, where you can clearly resolve 4 distinct populations. But just by simply changing the combination of fluorochrome, even though we use very good dye and bright dyes like B421 and B711, the spread that we have introduced into this panel does not allow us to resolve PD1. It's a blob. And in most cases, if you're not careful, we might get these results and not realize that we have a problem, and that will lead to inaccurate biological data interpretation. Therefore, it is absolutely critical before we design a panel, before we run an experiment, to be able to predict where spread could be a problem and deal with it. And we'll talk about how to deal with it, or maybe stay away from it altogether if possible. So how do we do that? And this is to introduce the concept of spillover spread metrics. So this was a concept and a tool that was introduced by Mario Rodere in 2013 into this publication of cytometry A. And the title of the publication was Quantifying Spillover Spreading for Comparing Instrument Performance and Aiding in Multicolor Panel Design. So before getting into the formula, let's just talk about mathematically what is spread. We talk about the difference between the negative and the positive population. The negative population will have a certain amount of background into this detector, and we can calculate that as a RSD into BUV737. And that's usually a function of electronic, of sensitivity. That's kind of noise, right? That's your baseline background. But now if you have a positive population and there is spread, you can see that there's an increase in the spread. So fundamentally, spread is nothing more than the delta RSD between the RSD of the positive and the RSD of the negative. So this additional signal here and here, this is added background that is coming from spillover. So the SSM formula, it takes into account the delta RSD as a true spread, but it also divides by the root square root of the delta MFI, which is the distance between the negative and the positive population. It's a function of brightness. And it's really important to understand that SSM was primarily developed to monitor instrument performance. That was the primary role of this tool, to make sure that different instruments from different laboratories are maintaining their performance and they perform equally. If you see variation in the SSM value, that will be an indication that something is going on with the instrument. How do we calculate SSM? That's another thing that makes SSM very popular. It's very easy to calculate SSM. On FlowJo, for example, you calculate your compensation and it automatically gives you a spread matrix. How do we read it? And this is very important. So let's take a minute here. We see these from multiple vendors, multiple scientists being used as the assumption is that a higher value of spread matrix correlates with a higher amount of spread. And indeed, you can appreciate that if you look at CD4 BB700, the way we read the matrix, the row will be our single stain, so our primary fluorochrome. The column are going to be the detectors that receive spread. So if we go across the BB700 row, when we see 0, sure enough, you can see that there is no spread, there's no additional background as compared to the spread of the negative. But when we go to 2.5, now you can appreciate that there's more spread. And as such, we use this color coding to tell us, hey, be careful if you're using BB700 and APC together, you might have spread. Okay, great. So to level set, let's launch poll question. Now we have that background in mind, and this will help us moving forward with this topic. So if you look at these three plots, we're looking at CD4 in three different fluorochromes: Alexa 4700, BUV 496, and PSI5. And then we're looking at, for each of these primary fluorochrome, a corresponding secondary detector, right? So if I were to ask you where the SSM would be highest value, would be A, Alexa 700 into APC H7, B, BUV 496, BUV 737, or C, PSI5 versus PSI 750. And remember, spread is the delta between the positive and the negative. It's when we see an added background on the positive population as compared to the negative. So,
Mirko, I've got the poll open, and we've got about 37% of people have voted, so I'm going to leave it open for a few more seconds here. Let's get that up over 50% at least, so people can vote.
Don't be shy. It's anonymous, and it's okay. Remember the assumption. Assumption is the higher value of spread, the higher the higher the value of SSM, the higher the spread.
And Mirko, I'm not sure if you can see those results, so I'll go ahead and read them to you, but we got about 60% of the audience voted, and 16% said A, Alexa 4700 into APC H7. We had 12% that said B, BUV 496 and the BUV 737. And we had the overwhelming majority, 73%, answered C, PSI5 into BUV 750.
That's great. Thank you for participating in the poll. And let me show you the results. As a matter of fact, the SSM is pretty much equivalent across these three plots. Actually, the one that many of you rightfully so were led to believe was the highest value as the lowest value. So don't panic. It's okay. That's why we're here. That's why we took the extra time to realize this is not working. There's something going on here. 0.7 would be considered as no spread if I just look at the metrics. But when we look at the real data, we may get in trouble. So it's a great thing you're here today because we're going to address this. But what does it mean that SSM is wrong or there's an error in SSM? And the answer is no. And we'll talk about why this is happening. But let's go back for a second to the concept of total spread. And we say that total spread is a function of multiple factors, spillovers, right? In this case, we have the same antigen density, CD4, the same fluorochrome, BUV661, so the same MFI in the BUV661. What is changing is the spillover value. And in this case, you will see that you have higher spread than here. Now, if we now keep constant the spillover value, because we're looking at PE into PCF594, the spillover value is the same. But what we're changing is the fluorochrome brightness as a function of antigen density. So CD127PE, roughly 1,000 receptor on the cell, gives you dim signal. CD4, 30 to 40,000 receptor, gives you a much brighter signal. So now you can see that even though the spillover, into PCF594, it's the same because it's still PE, the spread is different because we're changing the multiplier of the MFI. Similarly, and this is another great example, if we take two dyes, PSI5.5 and BB700, they're fairly similar in terms of spectral property. They're detected in the same detector, okay? But actually, if you look at the spillover value, CD4, PSI5.5, has more overlap than BB700, 52% and 35%. However, BB700, it's much, much brighter than PSI5.5. So now when we look at the total spread, even though PSI5.5 has a higher spillover, the much higher brightness of BB700 is responsible for contributing overall to a larger spread. And this is also why we talk so many times that looking at the spillover value that comes from your compensation metrics may be very, very misleading. So you should not look at that. Doesn't mean higher spillover value does not necessarily mean higher spread. So let's go back to the SSM. Why is this happening? And this is happening because the SSM, as I showed before, it's independent of MFI. By dividing for a square root of the delta MFI, Mario Roder and his team were eliminating for the equation the contribution of brightness or MFI to spread. And this was done on purpose. If you read the paper, it's very clear. And they did this because the main intent of this tool was to monitor instrument performance. So they want to eliminate any potential variable that will come from reagent or experimental setup. If you have a different batch of a reagent or a different donor, that will contribute to a different SSM. But if you want to monitor instrument performance, you want that to be independent of MFI. So it's a great tool for monitoring performance. But as you have seen, by virtue of removing or normalizing for the MFI, we're going to be less accurate in spread prediction because we're not taking account the multiplier. We're only looking at a part of the equation. So let me give you a practical example of why this is going to be a problem. So we design a panel based on SSM, and we want to focus, for example, on PD1, critical marker. We use BB711 as a bright dye, and we can also look at the spread into this detector. And you can see that if we look at the color coding, and this is our panel, we are not too worried. Overall, people say, you know, anything below 2 or 2.5, it's good spread. So we're good to go. Now you remember, this is how the panel turned out to be. So something went wrong. There was way more spread than we predicted. And by virtue of having FMO controls, we were able to identify that the spread was coming from BB700. When you remove BB700 from the panel, you can see that this goes back to normal. So how did we miss it? And that goes again, I'm reiterating the point that this is because we did not take into account fluorochrome brightness. Actually, per CPSA 5.5, even though the SSM value is higher than BB700, would have been a better choice because it's dimmer, lower MFI, lower spread. We make the assumption that low SSM would mean low spread, just like we did in the poll before, but we didn't take into account the brightness of BB700, but we also did not take into account the CD8. It's also expressed at higher level than CD4. So the spread eventually will be even higher than this. So that's the mistakes, and that's the discrepancy that all of us have been observing. And this brings us to the new tool. Nothing fancy, right? So we have understood that the problem is the normalization of the MFI. That in the SSM, it gives us a partial read of the spread. So what we introduce now is a total spread measurement, because we want to take the full spread coming from both the spillover and the MFI. We're basically taking the SSM value and multiplying for the square root of the MFI. So basically, we are eliminating the normalization. So now we're left just with the true delta RSD. So now you can see that in this case, where we see before, the SSM was unable to indicate the difference in spread from this plot to this plot to this plot, but the TSCM now will give us that increased value in this plot because it's taking account the brightness. SSM is not taking account the PISA 5 is much, much brighter than BV496 or Alexa 700. So now if we look at TSM value, it's more accurate representation of spread. I will just point out something here. You can see the TSM value here, 24.7, 25 are pretty much identical. Again, you may be misled visually because you might think that these has more spread than these. But remember, spread is relative to the negative population. So you can see that there's a lot of background into this detector, even the negative. This one is much tighter. So when we do this minus this or this minus this, the values are the same. Okay, let me run now through, again, the same concept, but we're going to reiterate just to consolidate that concept. So let's take a couple of scenarios. This is a scenario where we have spillover and we may maintain constant antigen density. It's all CD4. Fluorochrome brightness, it's all BUV661. We're only changing the detector where we measure spread. And in this case, since the MFI is constant, and the antigen density and the fluorochrome brightness are constant, the only variable is spillover. In this case, there is a direct correlation between spillover value, SSM, TSM, and spread. In this case, we can say that the higher amount of SSM value indicates higher spread, similar for TSM. However, if now we keep the antigen density constant, so CD4 for everybody, but now we're looking at different fluorochromes into different detectors, and they have different brightness. So we're going from dim to bright to very bright. Now what you appreciate is that the SSM is the same because these combination of dyes have the same level of spectral overlap. However, by virtue of having different brightness, their spread will be different. So this is another case in which the SSM will have not predicted difference in spread across these three values, these three combinations. But if you look at the TSM, you can clearly see that increases as you can see the spread. Again, this is to show that there's a correlation between spread and MFI. The higher, the brighter the signal for this, the higher the amount of spread. Same thing we can do for antigen density, right? We can keep the fluorochrome brightness the same, but as we showed before, we use a lower antigen density and a higher antigen density. When we look at the SSM, SSM is the same, the TSM is different. We can look at the opposite scenario. We have here P into PCF594, SSM of 4.7 that on average would be red, and you would say, oh my God, I cannot use these two fluorochromes together. But in reality, if you're using a low antigen density marker conjugate to P, you can see that there's no problem. The SSM is still high, but the TSM now came down also tenfold. And this also tells us that this is a way we can also handle spread. So if we have CD8 and we are now reducing the MFI by virtue of diluting the antibody, we can reduce the MFI. Yet again, the SSM is not changing, but the TSM will change to reflect the difference in spread. So now very critical to remember that we need to titer down the antibody to reduce the MFI. If we change the voltage into the per CPC 5.5 to reduce the signal, that will not have an impact on BU711 spread. Spread will stay the same. Okay, how do we use this in panel design? I already showed you that when we look at a single row, that assumption stands true, that higher SSM is correlated to higher spread because we have constant antigen density and constant fluorochrome brightness. But now we know that if you're looking at the different fluorochrome with different brightness, and we do compare two combinations with the same amount of SSM, the spread will be different. And this is a limitation for panel design. So SSM does not provide a total measurement of spread. The same value across different rows will translate into different amount of spread. So the color coding that everybody and all of us have been using really is meaningless, because 5 here is not the same as 5 here. So the color coding does not apply. We need to put in the context of brightness of the fluorochrom. And also it's telling us that when we run the spread matrix with CD4 as a reference, if we change the antigen, if we run now on our panel-specific reagents, the values will not change because you will not see the difference in the reagent and the antigen density. So you can under or overestimate spread easily. If we look at TSM instead, as you may be convinced by now, let's go back to this combination. The SSM was giving us 2.5 and 2.6. We clearly see more spread here than here. Well, that's reflected by a higher value of TSM. And most importantly, if I compare now two pairs with similar TSM, you can see similar spread despite different SSM. So this is a confirmation that TSM is a more accurate tool to predict spread. Now, there was a question that came during the registration I'm going to bring up here. It was, what's the acceptable value of compensation of metrics? And it's a great question because sometimes we get a little bit overwhelmed by this number. But let me show you here. So first of all, with TSM, since now the values are comparable across the matrix, color coding makes sense because we know that irrespective of the antigen density or the fluorochrom brightness, 250 and 228 will look the same. But this is a tool that's only informing us of where potential problems are, okay? We still need to apply good panel design rules to avoid or manage the spread. It doesn't mean that now panel design, I can use everything that I want. I still need to think of the biology, of the co-expression, and the level of expression, because this is calculated with CD4. So I know the CD4 BB700 will give me very high values of spillover here, of spread here. But I also learned that if I use CD127, this number will come down. So we really need to be cautious of our panel design. And to the question that came earlier, what's an acceptable value? I would say ideally you want to be in a situation where everything is green, right? So you can use this tool now to select only combinations that are green. But if you are in a scenario where you're forced to use all your detector, you will always have scenarios like this. It doesn't mean you cannot use BB700 and Alexa 700 because you have 970. You can still, that's still acceptable as long as you reduce the density of CD4 or put these two fluorochroms on two markers that are mutually exclusive, CD3 and CD19. If not co-expressed, there's no problem. So you actually can use this tool to see where the problems are and start from there and say, okay, these two are a problem. Let me put them on two markers on two different lineages. And you solve the problem right there. So the short answer is there's not really a maximum acceptable value. We can work with any value. It becomes a little bit more challenging because we need to accommodate for that change. Okay, the last couple of minutes, just gonna talk about panel performance assessment. So all that we talked so far, it's panel design. So usually we have a CD4 in all the colors that we use as a reference before choosing the fluorochrom to be matched with the specificities. But we can also run a matrix after we have ordered reagents, we run our panel. We can also now run the matrix with the panel-specific control. Can we use that matrix to assess the performance of the panel? And the answer is yes with TSEM, right? Because let's look at this example. This is what we use for CD4, all the colors as a reference. This is how we design the panel. Then we run our controls, okay? So our panel-specific reagents, they have all kind of different antigen density. So you can see that CD4PE, there was an issue with BOV615, but we knew that we were going to associate P with CD95, very dimly expressed. So the spread will come down. And as a matter of fact, when you run the TSM, now you can see that there's no impact whatsoever in this channel, as the data will tell you. So I can use TSM after I run my control with my true panel-specific reagent to make an assessment whether I got rid of spread. Well, the same you cannot do with SSM. And we see this being done, but by now you should be aware that the SSM values will not change when you change reagent because we're normalizing the MFI. And that's why we didn't catch this increase of spread into BV700 because the values stay pretty much the same. So we cannot use antigen panel-specific reagent to assess the spread on a panel because we're normalizing the MFI. And this is going back to our panel, right? The bad panel, we missed this problem with BV700, but if we ran TSM, you can see how the picture is completely changing. Things that were high spread here based on SSM, by virtue now using PD1, that's dim, the spread goes completely down, but not in the SSM. And we were caught now the big increase of spread into 700. And we can also then use this for assessing our panel. So this is a good panel. When we run the panel, everything is green. This is a panel that we have confirmation there's no spread into this panel. All right, so I want to leave at least a couple of minutes for questions. But before we wrap up, I also want to inform you that we have worked together with the Flojo team to implement the TSM into Flojo. So now you have the opportunity when you compensate and you have the SSM tab in Flojo, if you download the latest version of Flojo, you can get SSM, which is still valuable for monitoring instrument performance. But if you want a more accurate spread measurement, you can display and export your total spread metrics. It's automatic. You don't have to calculate manually. It's something you're familiar with. The only caveat right now, as of today, this is compatible only with traditional compensation, not with auto spillover compensation. Just as a conclusion before we open up for questions, I just want to reiterate, SSM has been adopted as a predictor of spread. It's a great tool, originally defined for instrument performance monitoring. It has some challenges and limitations that we showed you for panel design specifically, and some of these can be now overcome using TSM, more specifically for panel design. Last slide, I could not thank enough the fantastic team at BD, Bob, Alan Stoll, Aaron Tisnick, Stephanie Whitman, Eric Puffer, and Stuart Williams. A lot of brainstorming, understanding what was going on, the Flojo team that implemented this in Flojo, and a lot of help from key opinion leaders in the field to validate this theory, to validate this tool that helped us getting where we are today. And with that, I'd like to thank you again for the attention, and I know we have 10 minutes, so I'll be happy to take any question. And please don't hesitate to reach out also offline if you have additional questions.
Mirko, thank you very, very much. There was a number of good questions that came in, and a few of them that we'd like you to address the audience. Actually, the one on Flojo was one of the key questions that was lined up for you to address. There's a number of questions that have kind of come in that deal with the differences or the similarities and how spectral spillover is impacted by the adoption of spectral detection cytometry. Can you make a comment on the differences between the more conventional approaches and the spectral side and where TSM fits?
Yes, absolutely. First of all, I need to apologize. I'm not showing my face. I have a problem with the bandwidth of the internet, so you just hear me. It's a great question that we are getting more and more. And it goes back to the concept that I described at the very beginning. Whether you are using conventional flow cytometry or spectral flow cytometry, spread is spread, spillover is spillover. Those physical properties of the dyes are not changing. You will have different amount of spread. You likely will have different amount of spread for a given pair if you look spectrally or conventionally, because the way we compensate, the way we subtract the signal is different. We take the full spectrum versus a discrete portion of the spectrum. So you might have a difference in the amount of spread, but the beauty of TSM is that it's completely agnostic of whatever method you use. If there is more spread in spectral, it will give you higher value. If there is more spread in conventional, it will give you higher value. We've done this empirically. We have a platform that allows us to look at data, the same data, either through spectral acquisition or conventional acquisition, and we can see this discrepancy. For the majority of fluorochrome, the spread is equivalent, but there are some couple of combinations in which the spread is higher when we compensate traditionally, or where we compensate, or whether we do spectral and mixing, but that's still reflected by TSM. And the variation of filters, PNTs, those are all factors that influence spread. Even if you take two traditional flow cytometers with different power lasers, with different filters, that will impact the spread. But again, TSM, it's an absolute value. It would just reflect if there's more or less spread.
Oh, very good, Marco. Now we have another question that kind of blends together, the biology and how it could possibly affect TSM. And so the question that actually came in was one that dealt more with an intracellular protein, and it was, how would TSM impact a more variable marker, such as an intracellular cytokine, or I would imagine, an activation marker? And how could I take this into account when developing a panel?
Oh, that's another great question. The issue with the variable, that's a great point. The issue with the variable marker, again, if we look at the SSM, if we see an upregulation of a cytokine, we will not appreciate the increase of spread that will come with it because it will be normalized. The TSM will be able, so if you compare, for example, a resting T cell with a stimulated T cells, maybe different time points, and you see an increase in the cytokine expression, an increase in the MFI, the SSM will stay the same. The TSM will reflect that increase in brightness and potential increase in spread. So again, it's a more accurate point. And the way I would look at it is I always go for the highest condition. So take like a potent mitogen, something that really blast the cells with the highest amount of cytokines that you can, and that's kind of your worst case scenario. But now that if you work back to more physiological, if you want stimulation, your signal will be lower, your spread will be lower. But it's a great point because it really gives you that dynamic variation of spread as the intensity of signal varies upon stimulation.
Again, thanks, Mirko. So here's another question that's kind of in that same realm, because not all markers, in panels are activation markers. It could be that we're just looking for a specific subset of cells, or we're setting it up for a panel in sorting. And the question that came here is, because TSM considers antigen density, in FlowJo 10.7, does it require that you use cells stained with antigens from your panels as compensation controls, or can comp beads still be substituted?
Fantastic question. Thank you so much for the question. The short answer is no. Comp beads will do the job of calculating compensation, right? But again, usually the comp beads are very bright. It will be not reflective of the spread that you will get from a CD27 stain. So you can use comp beads as a surrogate of cells for purely compensation. But if you do want to assess the amount of spread in your panel, you must use the cell stain single controls with the same biological sample that you use for the test. Because the bead, you can calculate the TSM from FlowJo using beads as well, but the value of the spread would not reflect the value of spread in your panel.
Very good. You know, a question came in here from a different angle, an angle of quality control. So as what you've shown and developed here that gives us a finer detailed and better information, right? Or more defined information in terms of understanding spill and spread in your panel. Here's an interesting question about cell therapy. And that it says, how feasible do you consider the use of TSM in the analytical development and quality control space for cell therapy? And I would imagine, Mirko, it's, you know, a cell that was expanded, like a Treg or a CAR T cell, where you're really looking at the quality of the drug itself. It could be on that side. Maybe the question wasn't on the drug itself. Maybe it was on just the value of just following and a response in cell therapy. But could you comment a little bit about the enhancements of TSM in better quality control of experiments?
Yes, absolutely. Again, we have 2 minutes, so I'm going to try to be quick before they cut us off. Actually, this is a beautiful example in which SSM and TSM would be working together to ensure that quality control. The beauty of this, from the same set of control in FlowJo, you can create SSM, which will be your quality control for your instrument, right? And then you will have TSM that will tell you about the biology. So this will also allow you to see that if you're seeing a change in the performance of your assay, is it coming from your instrument that is, maybe the laser power is changing or something is drifting? SSM will tell you that. Or is it coming from biology because your cell line has now changed the phenotyping, has been activated? TSM will tell you that. So now you have both tools to really control your experiment and variation that could be either instrument related or biology related. But yes, if you compare the TSM across time points, you will be able now to see the variation if the level of expression are changing, that you will not be able to do with SSM. And that's why I wanted to make the point that these two tools are not, I'm not saying SSM is not useful anymore. They're complementary, they have different values, and they can be used together to control your experiment.
Okay. Mirko, I want to thank you very much. There were a number of other questions. We will address them and push them out to all the individuals that asked them. On behalf of BD and Mirko, thank you very, very much. I'd like to say thank you and then turn it right over to Jeff.
Yeah, thank you very much, Bob. I also wanted to say thank you to Mirko and to you, Bob, for presenting this new concept today. You could tell from the questions that came in that people find this fascinating and interesting, and it's just obviously going to have a big impact on the field. I want to send a big thank you out to BD for sponsoring this webinar and making it possible to share this content with everybody. And most importantly, I want to thank all of you for attending today and seeing this new information being presented. On behalf of everybody here at FluoroFinder, we hope the webinar has been interesting and maybe even enlightening for some of the flow cytometry work that you're doing in your own lab. If you have any questions, additional questions about today's webinar content, or any questions regarding BD products and services, please email us at support@florafinder.com. That's support@florafinder.com, and we'll be sure to send those questions on to get them answered by the experts here. So thank you again, everyone, for joining us today, and have a wonderful rest of your day, wherever you may be.
Thank you, everybody.
Bye-bye.